Hello, everybody. My name is River Fonseca, your TA. Today I will talk about the synthesis of acetyl salicylic acid, or aspirin. So aspirin is part of a family of drugs called analgesics, and they have similar properties. Some of them are antipyretic, which means that they reduce fever. They are anti-inflammatory, they're analgesics, and aspirin is actually a blood thinner as well, so it reduces the chance of having a stroke after a heart attack, for example. So they reduce the likelihood of stroke events or thrombosis events. So, so we'll synthesize it via an acyl substitution, which you'll be seeing in your organic lecture. So you have this compound, which is a diketone, and this carbonyl attacks the uh, hydroxide, the hydroxide group from phosphoric acid, and it cleaves it. So this hydrogen is recruited by the oxygen, and it ends up being with a positive formal charge. So then the dense electron structure attacks this oxygen, and so this carbon remains with a positive charge. And so in comes salicylic acid, and this highly polarized area attacks the carbocation and it attaches itself to it. This hydroxide becomes acidic, and this unstable structure grabs the electrons from that acidic hydrogen. So then, again, this unstable structure decomposes itself, and it actually happens the opposite of what happens in the beginning happens here. Instead of the oxygen grabbing this hydrogen, this proton, the electrons from the OH bond come down here and make the ketone. This bond remains with the other ketone, or well, with the ester, forming carboxylic acid, and this remains an ester, and that's how you get aspirin. And it's actually very quick and easy. So the procedure: you weigh 1.4 grams of salicylic acid. In your notebook, you should always keep track of the formula weight of your compounds, and therefore you have a quick calculation of the number of moles that you're working with. But you place this amount in a 50 ml Erlenmeyer flask. You add 3 ml. Again, you have to keep track of the molar weight of your reagents. So you put 3 ml of acetic anhydride in such a way as to wash down any material adhering to the walls. So you wash it down like this, all throughout the Erlenmeyer flask. And then you add 5 drops of 85% phosphoric acid. So again, the phosphoric acid is the reactant that kicks the reaction to begin, right? So then this works best in heat. So you heat to 85 to 95 degrees Celsius for 5 minutes on a hot plate. And after that's done, okay, well, you can have it actually in a water bath, but you can also have it directly on a hot plate. So there's different ways of doing this, right? Once that's done, you remove the flask and you allow it to cool, and you add 2 ml of water in one portion. However, you should be careful because acetic anhydride reacts with water kind of violently. Any excess acetic anhydride decomposes vigorously, and the contents of the flask comes to a boil. Again, once you add water, you have to add sometimes dropwise, depending on how much acetic anhydride you actually used. So you have to be careful. Afterwards, you're still going to promote the crystallization of a compound. So when you think that the composition of acetic anhydride is complete, you're going to add 20 ml of water, and you allow it to just crystallize. This is advantageous to you because you want to avoid recrystallization or any other follow-up techniques. So this is just to make your life easier. So if you do this correctly, you would simply have crystals without too much work. So you have to be on the lookout for crystals in your solution. So when they begin to appear, you place the flask in an ice bath, and this will hopefully quickly start creating more crystals in your solution. So eventually, after some time, crystallization will be complete. And then you collect your product on a Buchner funnel with vacuum filtration. You insert this Buchner funnel with an adapter here, and it has to be an Erlenmeyer with a vacuum connection. And you should usually put a filter that fits this Buchner funnel. You create the vacuum, and you just put your solution down here, and you wash with cold water and allow it to dry. It's important that you allow it to dry because you have to weight it. So if it's wet, you will actually weight not only the weight of your compound, but also the weight of water. So it's going to mess up your yield calculations, right? So you have to make sure that it's actually dry. So you just let it sit there drying for about 20-30 minutes, maybe more. So again, acetic anhydride is a dangerous reagent. It can cause serious respiratory difficulty. With a lot of compounds, you will always handle in the fume hood, and you should not get your face near these compounds. So do not breathe the vapors. It can cause serious permanent eye injury. You have to have your goggles at all times. It can cause serious chemical burn on skin. And if that happens, you wash with a lot of water and you alert me. This reagent reacts vigorously and sometimes violently with water. So you have to use great care when adding water, which is something that you do in this experiment. And you have to always keep in mind that hot solutions can be much more reactive. That's why you would use a water bath, for example, or a hot plate. And something that I have never mentioned to you until right now is that when you open a flask, it should always be pointed away from you. That also applies, for example, to the extraction funnel that you use when conducting extractions. So that's that. Again, you have to make sure that crystals are completely dry, and you have to know why, right? If you want to talk more about that, you should email me. For recrystallization, if you're not aware of what that is, you should review what that is. And you have your textbook to consult, or you can also consult with me again. After they're dry, you weight them, and you take the melting point of your crystals to actually make sure that that's your compound that you actually got. But that's only one type of evidence. You can also perform IR, which is infrared spectrometry, and NMR, nuclear magnetic resonance, to gather more evidence that your compound is the actual one that you want. We'll actually cover these later. And then you determine percent yield. Well, that's the end of the lecture. I hope you learned something today. Thank you very much.